to us about defining sets in full designs and full Latin squares.
Thank you. Before my talk, I wanted to give a quick plug. I'm part of the organising committee for a conference, the Australasian Conference on Combinatorial Mathematics and Combinatorial Computing, which is going to be in Rotorua, New Zealand, in December, 17th to 14th. So just Google that, you'll see pictures of Rotorua that are so beautiful. You'll be persuaded to come. So the registration's now open for that. Okay, today we're talking about, I'm from the University of Waikato, which is in New Zealand, not too far from Rotorua. I'm talking about defining sets of full designs and full Latin squares. So these are two analogous things, or analogous. Right, so we're going to talk about, firstly about Latin squares, because they're easier to explain, draw diagrams for, but if you're more excited about designs, just be patient, we'll get to them, I promise. Okay, so well, we've got the idea of a n Latin square. So here are 2, 3 Latin squares, and essentially it's easiest to explain by example. You're allowed multi-sets in a cell, and you've got to have each of the numbers 1 to 3 occurring 3 times in each row and 3 times in each column. So the full one is just the only way you can do it without any multi-sets. So you just put numbers 1 to 3 in every cell. Of course, there are other ways to do it if you have multi-sets. And then we can have a partial such structure, and this partial structure completes to both of these, so it's not a defining set. Right, so when we talk about the defining set of a full Latin square, it's with respect to it being an n Latin square. So the condition when we complete these is that each number is 3 times per row and 3 times per column. Okay. So here are a couple of things that are minimal. They're not just defining sets, they're minimal defining sets for the full Latin square F3. So this one, it's a pretty easy Sudoku puzzle. This one's slightly harder. Sudoku type puzzle. So let me see if we. You can prove that you have to have at least 1 in each of these cells, so you have to have exactly 1 because there are 3 ones and so on. So both of these are minimal defining sets. And this is kind of the smallest one we know of in general. We can generalize that one there. So the question is, the problem really is what's the smallest you can make such a defining set? And the answer throughout this talk is going to be any defining set you have asymptotically is, you really have to take almost all of the square. So that's the result we'll have in a few different guises in this talk. Right. So where are we? So the smallest ones we know of are this size here, and minus 1 cubed plus 1. So that's generalizing that structure there. We call them saturated if each cell is either empty or is full, i.e. has all the possible symbols in it. So this one's a saturated one, this one's not. And if it's saturated, we can say this size exactly. So what's going on there is if I have, for example, we're thinking in the complement of the defining set. If in the complement of the defining set I have something like this, which we'll call a cycle, then I can switch those 1s and 2s around to get another completion. So you can't have this. So it's a forbidden structure in the complement of the defining set. So in the saturated case, what that kind of means is we don't want a cycle of empty cells, and that forces the number of empty cells you can have. If you think of the graph associated with that, where you have vertices, bipartite graph, vertices for the rows, vertices for the columns, and you put an edge of that cell is empty, then that graph can't have any cycles. So in the minimal case, it's a tree. So you put a tree on, and that quickly gives you the defining set size. So the most recent result is showing that, in fact, the minimum possible size is the most lovely formula here, which comes from Lagrange multipliers, and it's much more likely, that's unlikely to be the real correct result. I guess it's probably that one there. But what we've shown essentially, combining these two results, you get defining sets really take up almost all the possible. So the size we're talking about here, so this would have size 12, that has size 9. We're counting the total number of entries there. So here, generally, you've got n cubed entries to start with. So your defining set has to use almost everything, basically. So your full defining sets, they're pretty full, in other words. So how did we prove this result here? Well, we got this idea of a trade, which is like a cycle. So going back to the example we had before, this isn't a defining set. I don't know if you can see the bold numbers here. With the bold numbers we swap around to get a different n Latin square. So the idea is we can't miss any trades if it's a defining set. We've got to hit them all. So I'll go back to that previous slide. So what we do, you've got d is your partial n Latin square, and for each pair of symbols, you define SAB of D to be the set of cells which contain neither A nor B. And we know that amount is limited because you're not allowed to have any cycles in the complement. So the most number of cells you can have in that trading cycle is 2n minus 1. So for each pair AB, we have that. They're just not considering a pair of elements. Right. And then what we do is some double counting. So we'll let Eij be the number of symbols in a particular cell, so you get the size of the defining set by adding over all the cells and what's going on here. So for each cell, we count the number of pairs of symbols which do not occur in that cell. Then on the right-hand side, we're counting n choose 2 for the total number of pairs of symbols, and for each of them, they can occur almost 2n minus 1 times. So we get this inequality here, and that's where the result comes from. So then we apply, we think of all the Eij's being variables, and we just maximize or minimize the function according to that constraint. We get that's where you get this result here. Okay. So we've got so why might you study full Latin squares? Well, so what you can do, you can take your favourite defining set of the full Latin square, you can take your favourite Latin square, and then you intersect them, and you'll always get a defining set for that Latin square. So the initial hope was these full Latin squares will tell you a lot about defining sets of individual Latin squares. And somehow the way I think of it is that in your full Latin square, you've really got all the information about every Latin square in there. So every Latin square is contained in there, and particularly every type of cycle or in general a trade is also contained in it. So We haven't been able to use it to find results like bounds on the smallest defining set size for a Latin square, but with properties like this we can study defining sets and squares. Right, so now we can go on to, we've got plenty of time here. We started at 10 minutes ago. Yep, so we'll go on to the analogous problem for designs. So a design, if you know Charlie, you'll know what a design is, but it's a collection of subsets, each unordered pair occurs in the same number of blocks. And your full design, what you do is you take every possible subset. So we're going to take every possible subset of size k from a set of size v. And then if I look at each pair, well, you fix a pair, and then that you've got k minus 2 elements to choose in that block, and they must be one of the v minus 2 remaining elements. So the full design gives you a vk, v minus 2, choose k minus 2 design. So here's an example, f6,3. We're just taking all the three sets, the subsets of size 3, set of size 6, but we can, by allowing repeated blocks, we don't allow, by allowing repeated blocks, I can get another 634 design, where, so for example, if, let's do some error correction. Can somebody give me a pair of numbers between 1 and 6?
3 and 5.
3 and 5, so we should find them 4 times in both cases. So 3 and 5, we've got here, 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 and here. It's 4 times. And 3 and 5 again will occur, should occur 4 times in here. 1, 3, 5, 2, 3, 5, 2, 3, 5, 3, 5, 6. Right. So when we talk about a defining set of a full design, again, we're allowing completion to a design with the same parameters that may not be simple. Okay? Right. So a lot more work has been done on full designs than full Latin squares. Work by the late Anne Street, and Gray, by Akbari, Maimoni, and Mysuri. So a lot of different constructions are around. And Diane is here, the February Waterhouse, they found this is the smallest size defining set size we know, and the block size is 3. And they also looked at, well, what's the minimum possible defining set size, and they got this result here. And in their paper, they conjectured for defining sets of full designs, the proportion of blocks in the complement will asymptotically approach 0. And it turns out this is true. And not just for 3, but where v minus k tends to infinity. And it's the same idea. There's a few differences, but it's the same underlying idea for what we did for Latin squares. So here, what we do, our SABD now becomes, so what you do, you fix, so you fix your A and B, and you want to look at the number of unordered pairs ij such that neither ija nor ijb is an element of D. And you get that there can't be too many. Right? If there's too many, we can do some sort of trade. And in fact, to get this bound, we had to prove an elementary result in extremal graph theory. It was so elementary I couldn't find a proof of it. I wrote my own, but we had to show that a graph with v vertices and more than roughly 4/3 v edges is guaranteed to have an even circuit. So, and that circuit guarantees a trade here. in the complement of this defining set. So basically, moral of the story is you can't have too many, if you fix your pair A and B, you can't have too many pairs IJ such that neither of these occur in your defining set. And similarly to before, we do some double counting. So what we do over here is we're looking at for each, so this is the case with blocks of size 3, so we're fixing the IJ over here, and then Xij is the number of triples which contain both I and J, so we're interested in, well, how many times C and Xij, so, right, so we're looking at the non-occurrence of pairs, which is why we subtract here. And then this also, we can count this in another way. We're going to do the pairs of elements A, B, and from our previous work, was V choose two such pairs, and in each case, we can't have too many of them. So again, we end up with a minimize this according to this constraint, so we can use required multipliers. And this is the result you get when the block size is 3. So we've got an asymptotic result. I mean, maybe the next problem I think will be to work to improve that function. Again, that's not going to be the smallest possible size. It's probably the one Diane et al. Found. And then we can sort of plug this result in when the block size is bigger than 3. And what's going on there? Well, your full design of it contains every subset of size k, right? So if you think about it, it contains many copies of all the full designs of smaller orders. So you kind of fix a certain number of elements, and then you can plug back in the result of the previous slide. And, counting that way, you get that defining set for any full design is pretty full. In Vichu's case, the total number of blocks, so we're only taking away a small number of them. Right. Yes, so everything I'm working on at the moment, I seem to end up using Lagrange multipliers. I don't know why. Do any of you know who knows the movie Grease? Some people in here. A lot of people don't. So there's that, you know, at the end where they're singing "You're the One That I Want," and well, I had this earworm in my head instead of I've got chills that multiply. I've got Lagrange multipliers, and I'm using them to control the function I'm analysing. It's maximising.
Sing it. Sing it.
Thank you.
Are there any questions?
What happens if v minus k is bounded rather than going to infinity?
I do not know. Well,
You haven't thought much about that.
no, I haven't thought about that.
Is there some sort of complementation thing that goes on there?
How do with B minus K is bounded? I
Yeah.
haven't even thought about that.
Yeah.
Oh, that's good.
Any other questions? All right, well, let's thank our speakers. The next talk will be downstairs in 5 minutes.
I didn't quite understand right now. Didn't quite understand. So you were talking about beginning with, we're beginning with the diagram.
Oh,
eventually able to decompose into a well-linked
Right, yeah.
So that's
So all that. But I think it was the very first one that watched, but of course, some of the other kind of nine.
so I guess such, just remember such
Yeah, you want it to really
extreme would be.
Yeah. Is that
Yeah.
Yeah.
Okay.